Hello, IB Environmental students. Today we're jumping back into the IA talking about data, the results, analysis, and conclusion section. We sometimes call this the RAC. Let's talk about it. So just like all other IA submissions that we do, the expectations are high, their rubric is tough. So we will talk about in class, on Blackboard and or Google Classroom, how grade conversions will work. So make sure you keep a lookout for that. You guys are rock stars and super stars, so keep in mind it's tough, but you can totally do it if you're looking at all the resources and practice examples, etc., doing peer and self-editing. Let's do it. So the results analysis and conclusion section has three major aspects. They are as follows: is able to construct diagrams, charts, graphs for all relevant quantitative and or qualitative data appropriately. Does analyzes the data correctly, completely, so all relevant patterns are displayed. That part is important. We call that the analysis part. That's 2 points. The other stuff was 2 points too. Aspect 3 interprets the trends, patterns, and relationships in the data so that a valid conclusion to the research question is deduced. This is us going back to the original hypothesis and deciding whether we should support or reject it based on what the data are telling us. So we're going to talk about each of these aspects, and keep in mind that if you had anything that you needed to change or edit in your earlier sections, the context or the planning, you're going to need to edit that eventually for this next submission too when we add in the RAC section. So let's talk about the RAC, starting with the raw data. This is the first part of aspect 1. Raw data can be really easy to have some funny errors. There's really weird things to make it awkward if we accidentally cut things off across pages. Let's just be smart. Let's just also be good communicators and check our stuff before we submit onto Turnitin.com eventually. We don't want anything awkward in our tables or formatting. This is just an overarching thing to be smart about. Please note when I go over a couple of things later that there's certain really good ways to write and communicate table formatting. We're going to look at a lot of examples. Be smart. It's super awkward when you repeat the same thing like a unit. Put it in the title. Put it in here. Be smart. So please, 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 as I talk about details here, listen and note them. So here's the first part, raw data. We can have quantitative raw data, and most of us do, right? And have to describe it somehow. So as we have quantitative raw data, we need to make sure whatever our quantitative precision and number of significant figures is staying the same. So if we have 2 numbers after the decimal place, keep it consistent. All right. If there's something that only had 1, put a 0 after it. If it was 3 decimal places, fine, but most of us never had anything to this level of precision. And some of us actually might have only had 1 decimal place. This is super important because later we're going to talk about uncertainty. When we make a title for our table, it must be descriptive. We should number our tables, such as table 1, and all columns should have titles, units, and errors next to them. Alright, so for instance, here's a good title: the relationship between the distance along a 25-meter transect from a stream when we have 5 trials, and the soil temperature, and it has the units, and the uncertainty of the measurement for that thermometer. So here's another example. It's different. This title isn't as strong as the one just presented as an example, but notice when we talk about raw data, it is really important that our number of digits is consistent. Now this person looks like they have a final digit of a 0. I'm not actually even sure they should really have that digit there because I don't even think the probe measured out to that level of precision. Alright, if you're not clear about the level of precision of your measurement tool, please let me know, and I would love to talk to you about your precision and uncertainty that you can include in either your title or your actual table, because that's super important. Here's another one. This person has a better table title. They have their units. Notice that that last digit is actually changing. So this person looks like they were measuring actually to that level of precision. So this is a much better table than the first one. And we can see units in the title. All right, their IV isn't in units. This time it's qualitative IV. This person ends up actually probably graphing in a bar graph. All right, the next thing, qualitative data. I actually have to present some of that too in the form of raw data in an organized format. For qualitative data, I can use tables or bullets, but I need to be organized in how I communicate that. Consider what things you saw: organisms, smells, cloudiness, etc. Anything that's really useful. You might even consider also making tables of other quantitative data that might affect your results, such as what was the climatic data around when you did your field work, such as sunlight, temperature, other weather data. Make sure you cite the source you used for that in your title. If you have any photos that are representing those qualitative data, please make sure that they have figure titles and that you are having descriptive captions that showcase what is being shown there. Never have a photo without telling me what the photo is supposed to show me. Otherwise, I have no clue what you're using that photo for. Photos and qualitative data can go in an appendix if you are worried about word count later in the year. Data processing and overview and sample calculations. This is how we describe how and why we pick the data types of processing we did, examples of every single type of calculation. So here, this one is our example IA we did a long time ago on mark and recapture. Notice that they are presenting out the types of calculations, both percent error, and they describe why they did what they did. But they didn't really tell me much about why they decided to use each type of calculation, so this person lost some points. Here's another one, but this time they tell me a little bit more and they give me a little bit more in their example. All right? Here's a really good one for an actual IA. This person tells me why they did what they did, the types of equations they used, and they give me an example of each type. We will look at this type of stuff more in class, but this is a section that's easy to do as long as you do it. Process data tables. Now I need to make sure that these process data tables are in the main body of my report. I need to make sure that they have good titles, just like my raw data with headings and uncertainties. I need to keep my decimals consistent with whatever I had previously. So we saw an example earlier in the year when we did our practice on mark and recapture. All right, that was the example of a process data table, averages and percent error. For most of us, for the IA, it's much more likely to be averages and standard deviations. I need a table number here, which isn't here, and then I need a descriptive title. This one is missing some clarity, but it's a good start, etc. So all good stuff. Here's another one. This one's even better. Tells me length of time they did their experiment, uncertainty for their tool. Very, very clear information. And these process data tables are super important because they end up gearing us up for our graph. Graphs are always of process data only. Here's an example of a terrible graph. This graph is terrible. Why? Because it doesn't tell me any trends, because it's graphing the raw data. So make sure not only you do the process data, you pick the right type of graph. Most of us are not going to be doing a pie chart. Only a few of us might have a reason to do that. Please check with me if you think that's what you want to do. So most of us are going to be doing either bar graphs or scatter plots. But what we really want to make sure each of these things has is a axis label. This is an okay start, but this one doesn't have measurement uncertainty. It really should. If it doesn't have it on the actual axis, it really should have it in the title of the graphic. So this one's a lot better because here we have the measurement uncertainty on each of the different things. All right, but this one has error bars here, which is really good. Usually the error bars are either going to be the measurement uncertainty or they're the standard deviation, which is even better. But I'm not even told which one is being used here, which is really bad. Descriptive figure title, at least that's starting to happen. And a scatter plot needs a line of best fit and an R² value. All right, and we're going to talk about what those things mean a little bit more in a moment. All right, here's another one, but this one is a bar graph, which is going to be used for qualitative things much more. So if I didn't have a numerical IV, this is what I would do. This one's telling me that standard deviation is the error bars, which is a lot better. And it also tells me the amount of error. All right, so this one's a pretty good one for a bar graph. Next section, we finally made it to aspect 2. For aspect 2, I'm analyzing the data. We're going to be looking at a lot of exemplars in class and grading them together. But here I'm talking about the major patterns and trends. I need to use terms like increasing and decreasing, but I have to actually note specific examples. Notice here they're using specific actual examples from their process data. Justify if you omitted any anomalies from your processing and explain why you used what error bars you picked if you used standard deviation versus measurement uncertainty and why. All right, so notice here that they are also talking about the error bars a little bit more, and the error bars might also be showing an overlap or a lack of overlap in the error bars. So if error bars do overlap, it means that the average in the average process data between two levels of IV are very similar because they do overlap. This means a future conclusion cannot fully be supported or rejected, and we'll talk about that more in class. If the error bars do not overlap, this means that the calculated process data probably are a little bit more different, and this leads us to stronger ability to support or reject our original hypothesis. So we'll practice that in class. That's a little bit tough. This person said, hey, my standard deviation is kind of low, and so that means I can kind of strongly support my data. All right. Scatter plots should all have an R-squared value. R-squared value is right here. If you have that in your scatter plot like you're supposed to, you also need to discuss what it means. Here's what that stuff means. An R-squared value that's closer to 1, this one's 0.641, which is kind of in between 0 and 1, means the data is really accurately following that trend. You are welcome to use a linear trend line or other types of trend lines to represent your data. You just have to describe what the other types mean. This linear one means it's a consistent increase. All right, but this one is not that close to 1, meaning the data actually doesn't really consistently follow this trend, which makes sense because this point's so much lower. All right, closer to 0 means there's little trend in your data. So some of these things are following the trend. It looks like this one's an anomaly, and I wish she had talked about it more as an outlier. And this would have been a perfect place to talk about that in her results and analysis section. Last but not least, make sure you don't discuss totally the meaning behind your data. We're not really doing a discussion or an evaluation yet. We're not making sense of what the potential consequences of the data are. Last but not least, the conclusion. In my conclusion, I need to restate my research question. I need to restate my hypothesis. I need to talk about, well, what does it mean? I might repeat some of the data that I used that represented trends, all right, and I decide to support or reject, and I think about support or reject in the context of how strong my uncertainties were in my error bars. All right, error bars could have been standard deviation, remember, or measurement uncertainty. All right, so here's that again. That strength of support is based on the error bars or measurement uncertainty. Then this should tell us how accurately we can really have our conclusion support or reject. Is it really reliable? So we'll practice this in class. All right, we're going to all kind of peek at stuff. So this is a better example of this being done. So this person has a research question. They talk about some key trends in the data. All right, and then in their error analysis, they say, all right, my error bars are kind of small. I wish they had done standard deviation as their error bars. All right, and that they should have talked more about the impacts. This person actually does not get full credit on their conclusion because they have not really talked about really what this does to my reliability of supporting or rejecting the conclusion. Last but not least, make sure again that you're using specific data examples. This person is doing that. You could refer to specific parts of your charts and tables. Figure 1 shows, Table 3 shows, and specific data points. Talk about why things are overlapping or not. Be as specific as possible. That's why you had all those data earlier. All right, this person also didn't do that, so this is not as strong. So we will look at some better, stronger examples of this being done in class. Wonderful job, guys. You can do this. This section is tough, but we will practice together.